All right, so welcome to today's class, and we'll be looking at this concept that I've written on my screen here, which is latent heat. So it's a continuation on thermophysics. Remember, last week we were discussing specific heat capacity, or in general, heat capacity, where we talked about the energy that is required to raise the temperature of a substance by 1 degree Celsius, or when it comes to specific heat capacity, we described it as the thermal energy that is required to change the temperature of a unit amount. So it is specific in its explanation to say we're just getting a unit amount, or we can say 1 kg of a substance by 1 degree Celsius. So the temperature or the energy Q that is going to be required to raise that substance's temperature by 1 degree Celsius, or the energy that is going to be released when that substance's temperature drops by 1 degree Celsius. We call that uh, concept the specific heat capacity or heat capacity in general. Now, in continuation, today we are going to be looking at what we call latent heat, of which this term latent heat just means hidden heat. Latent actually means hidden. Just increase the size of my pen. Okay, so unconcealed or hidden heat is what we call latent heat. So what are we exactly focusing on when we talk about latent heat? So remember, um, substances or matter falls into three different states. There's what we call the solid state. There's what we call the liquid state. Whilst there's also what we call the gaseous state. And matter can actually transition from solid to liquid, also from liquid to gas. So if we have a solid, if it's a solid substance, the amount of heat energy that is going to be raising the temperature of this substance by 1 degree Celsius, we're going to be calling that substance what? The specific heat capacity, of which you say this is C of this solid. The same happens when we're talking about the liquid only internally. The energy that is going to be changing the temperature or raising the unit temperature or uh, unit substances amount by 1 degree Celsius, we're going to call it the C, which is the specific heat capacity of your liquid. The same on the gas. When the gas increases in temperature, we can say the same. Now, what happens when a solid wants to transition from its solid state to a liquid? To say there's what we call um, melting that is going to take place. And in order for this substance to melt, it's going to take thermal energy that we're also going to call at Q. Remember, thermal energy is always represented by Q. And also, when you want to change the state of the temperature, if you continue supplying this temperature with thermal energy, it is going to transition in its uh, state from liquid to gas. And this heat that is required to change the temperature or to change the state of this liquid from liquid to gas, we're also going to call it Q, required to change the temperature of heat, or I mean to change the state of the substance from liquid to gas. So what am I trying to talk about here? I'm trying to relate all of these things to what I'm calling latent heat or specific latent heat when we want to talk about the specific unit of a substance or unit amount of substance. So how can we describe latent heat? Let me just write the description here. We can describe latent heat as uh, the energy absorbed or released. Remember, this is a two-way equation or a two-way reversible equation. So it's energy absorbed or released. Or released during phase change. Phase change. And this is going to happen at a constant temperature. Okay, so that is what we are calling latent heat. So when you're changing the phase of a substance, there's energy that is absorbed. Some of you might wonder why we're saying the temperature is constant. Where is this temperature going, or why isn't the temperature increasing since there's constant supply of thermal energy? It's because whatever phase you are having, if you are heating a substance, let's say you are heating a solid, there will be temperature. In order for you to change the phase of that substance, there will be heat energy or thermal energy that is going to be absorbed internally by that system without raising the temperature. And that thermal energy is actually going to be used to break down the bonds, to break the bonds that are within that state of a substance, to put or to make the particles to be further apart from each other, thereby changing its state. And that thermal energy, since it is absorbed, it's you can't it or it isn't seen because it is absorbed. There is no measurable change in temperature when there is phase change because the energy is absorbed to break down the bonds or the cohesion forces, the intermolecular forces that are between that particular phase of a substance. Hence, we are going to see that the temperature is constant. So that temperature now, or that thermal energy that is required to break or to change the phase of a substance, or that is released when there is change of a phase of a substance, is what we are calling latent heat. That is what we are calling latent heat. And if we have these phases, we say there is solid, there is liquid, and a gas. Let's notice that you can change a solid to a liquid, and you can also change a liquid to a gas. Whilst also you can change a gas to a liquid and also a liquid to a solid. So here energy is released. So here energy released. Whilst on the top part, the opposite is happening. Energy is absorbed in order for you to change the the specific latent uh, heat or to change the phase of that substance. Sorry. Okay, so how can we calculate this uh, guy that we are calling the latent heat of a substance? So there is an equation that is going to relate us to this guy that we are calling latent heat. So it is represented by the letter L, represents specific latent heat of a substance. And you're going to notice to say this, or when you have Q, when you're supplying thermal energy, then there's change in phase. The thermal energy that is going to be absorbed at that particular point is going to be directly proportional to what? To the mass of that substance and the latent heat of that substance, which is the energy that is the actual energy that is required to change the phase of that particular substance or to change a unit amount of that substance's phase. So the heat that you're going to supply is actually directly proportional to the mass of that substance and the latent heat that is required. And from here, we can make latent heat the subject of the formula by dividing both sides by mass, which is going to give us an equation which will look like L, which is latent heat, being equal to Q, where Q is the amount of heat energy, over M, where M is the mass of that substance in you can either use kilograms or grams depending on the units that you've been given. So what are the units of specific or latent heat or specific latent heat? You know, to say energy is in joules, Q is in joules. We bring back dimension analysis. First mass is in kilograms, or I've said here we can also use uh, grams. First heat here we can also use calories. First even here we can also use what? We can use grams. So it depends with the units that you've been given, but I can say the SI unit for latent heat are what? Are joules, which is joules per kg. Like this. These are the SI units for your latent heat, but you can also use calories per gram. It depends with just the units that you've been given. Okay, so we've described what latent heat is, but since we've described two phase changes, where we've said there's change in phase from a liquid to a solid, and we've also, from a solid to a liquid, we also talked about the change in phase from or between a gas and a liquid. There are also two types of latent heat that exist. And what are those types of latent heat? There's what we call latent heat of fusion. Latent heat of fusion. And what is this type of latent heat or what does this type of latent heat actually talk about? So this is the heat that is absorbed or released when matter or when there is change in state. So I'll just say change in state between solid and the liquid. So when there's change in state between solids and liquids, the amount of energy that is going to be released or absorbed is going to be called what? It's going to be called the latent heat of fusion. So it is going to be released when you're changing from liquid to solid, what is going to be absorbed when you're changing from solid to liquid. And so long as it's dealing with the phase changes that are taking place between solids and liquid, we are going to call those that latent heat the latent heat of fusion, and it is represented by LF to represent latent heat of fusion, and this is equal to what? This is equal to the thermal energy that is supplied or absorbed or released. I mean, that is supplied, sorry, over the mass of that substance. So it is represented as latent heat of fusion, LF here. And the second one is what we call latent heat of vaporization. But we should talk about this one when we're talking about water, latent heat of vaporization. Latent heat of vaporization. And this is the thermal energy that is absorbed or released when there is phase changes between liquid and gas. So this one is taking place between liquid and a gas, and depending on what is happening, it is going to be either released or absorbed. So it is going to be absorbed when you're changing from a liquid to a gas, what is going to be released when you're talking about phase change from a gas to a liquid, and it is represented by R V being equal to Q, which is a thermal energy, over M, which is the mass of that particular substance. So these are the two types of latent heat that you are supposed to know. There's latent heat of fusion and latent heat of vaporization, depending on which two phases are actually interchanging between themselves. So now that we understand the types of latent heat, we know the formula for latent heat of fusion. We know the formula for latent heat of vaporization. What we should know now is that in a case where we've been given the actual scenario, let's say they've given you to say, let's say there is ice. They've given you ice, which is at negative 15 degrees Celsius. Then they've told you to say this ice is heated until it turns into a gas. What is going to happen? You're going to have a graph like that, where here you have temperature, and here you have what? You can say you have time, as time is passing. So if you have been given this ice at negative 15 degrees Celsius, you know today this is a solid state. This is water. And the temperature is going to increase. And you know to say ice melts at 0 degrees Celsius and water freezes at 0 degrees Celsius. So when it reaches at 0 degrees Celsius, this temperature is going to remain constant until there is a change in phase. Once this water changes, or once this ice changes from solid to liquid, the temperature will start rising again. Then water is going to boil at what? At 100 degrees Celsius. Like this. It will start boiling and it will turn into a gas. Then the temperature of the gas can keep on increasing like that, the temperature of the gaseous water. So you can see to say at this point when there's phase changes, the temperature is remaining constant due to the fact that we already talked about. So there is heat that is absorbed here, there's Q here, there's Q that is absorbed here, there's Q that is absorbed here, and also Q that is absorbed here, also even here. So what you're going to notice is that the Q that is absorbed here will be the amount of energy that is just increasing the temperature of a substance by 1 degree Celsius. So as time is moving, you're going to find that the formula for Q that is at this phase is going to be what? It's going to be equal to M multiplied by C, which is the specific heat capacity of the ice, multiplied by the change in temperature. We already looked at this formula last week. Then what about here? Here we are having um, energy that will be also absorbed here will be due to the latent heat of fusion of that substance. So the energy that will be also absorbed at this point is going to be equal to the mass of this substance multiplied by latent heat of fusion, like that. Here, you are increasing the temperature of water, so we'll be having M, specific heat capacity of water, multiplied by change in temperature. Whilst at this point, we're also having latent heat of vaporization. Hence, this will be equal to mass multiplied by what? Multiplied by the latent heat of vaporization. Whilst here, you'll be increasing the temperature of a gas, so you can uh, put these formulas or put gas in short. So let's just say this, the Q here will be equal to what? Will be equal to the mass of that gas multiplied by C over the gaseous water multiplied by the change in temperature, like this. So those are the different parts of a graph that is showing you um, the different properties of latent heat of vaporization and also latent heat of fusion. So there's temperature or there's amount of energy that is absorbed. And as that energy is going to be absorbed, there will be no change in temperature. There will be no increase in temperature because that energy is actually absorbed to break down the intermolecular forces that are between that particular substance. So where can you apply this knowledge that we just talked about here? So in a case where maybe you've been given two, let's say, can I give an example of two different states of water? Or even two, oh, I already talked about two liquid waters at different temperatures when I was talking about specific heat capacities. So now let's imagine we've been given two different phases of water at different temperatures. Let's say we've been given ice at negative 15 degrees Celsius, and you've been given what? You've been given water at 30 degrees Celsius. You mix these two substances, then you're asked to say what is the equilibrium temperature. Because you know to say when you mix two substances at different temperatures, you are going to experience transfer of thermal energy from a substance that has higher temperature to a substance that has lower temperature until they reach at the same temperature that we call the equilibrium temperature. So in case they ask you to say what is the equilibrium temperature here, what are you going to notice? You're going to notice to say this water, which is at negative 15 degrees Celsius, what is supposed to happen to this substance? Or how many amounts of heat are we going to have? We're going to have three amounts of heat or three different types of heat. We're going to have what we call Q1, Q2, but also what we call Q3. And how are these Qs actually distributed over this graph that we've just drawn here on top? Here, you can see the Qs that are here, which are just showing us the actual heat. So where are these heats actually coming from? You're going to notice that in order for this ice that you have here, or maybe before we talk about the ice, we said uh, for equilibrium temperature to be reached, you're going to notice that Q that is gained will be equal to Q that is lost, or negative Q that is lost. So since we have this Q that is gained is going to be gained on the part where we have the ice, you're going to notice that we will need Q to change the temperature of the ice from negative 15 degrees to 0 degrees Celsius, like this. And this temperature or this heat, thermal energy, we're going to call it Q1. Then there will be another Q that will be required to change the state of this water from solid to liquid. We're going to call that Q2. So there's Q1, there's Q2. Then there will be another Q which will be responsible for taking this temperature of the water from 0 degrees Celsius after it has melted to an equilibrium temperature that we don't know, like that. We're going to call That's temperature Q3, like this. Whilst on this side, we're just going to experience the change in temperature, or there will be Q that is going to be lost due to the change in temperature. From what? From 30 degrees Celsius to a final T that we don't know, like this. So that means we're having four different types of heat. Three types of heat from this substance which is experiencing change in state, whilst one particular thermal energy or heat on the part where we're having no state, no change in phase. So even when we want to plug these into this formula, what are we going to do? We're going to notice that I will have on the left hand side, what did I just do? Okay. So on the left hand side, we're going to have Q1 plus Q2 plus Q3. This will be equal to what? This will be equal to negative Q4, like that. Remember, I told you how to remove this negative in a case that you want to remove the negative. But in this case, I'll just maintain it like this. And Q1, since it's responsible for changing the temperature of water, we're going to say Q1 is equal to what? Q1 is equal to MC of ice multiplied by change in temperature plus Q2 is the temperature that is responsible for changing the phase of that substance. Or changing the phase of that substance. So I'm going to say Q2 is equal to what? Q2 is equal to mass multiplied by latent heat of fusion, like this. Plus Q3. What is Q3? Q3 will be equal to mass multiplied by specific capacity of water now, multiplied by the change in temperature, like that. And this is going to be equal to what? This is going to be equal to minus mass multiplied by specific capacity of water multiplied by the change in temperature, like this. So this is going to be equal to what? So let's put a scenario whereby maybe they've told us to say the mass of our water. Let's say they've told you to say the mass of the ice is 10 grams. This ice that is on the left hand side. Then they've told us to say the mass of the water that we have here on the right hand side is 100 grams. Okay, like this. What are we going to do now? We're going to say 10 grams here multiplied by the specific capacity of water. The specific capacity of water is something that you can memorize, but in most cases, they are actually going to give it to you, and that's not a very big deal. So you can convert your grams into kilograms just to avoid mistakes. I'm going to say this 10 grams into kilograms. I'll divide this one by 1,000, and I'll get this 0.00 grams or 0.01 kilograms. On the ice, this one, the water, I'll get 0.1 kilogram. So I've managed to successfully convert. Now you can plug them in. You can say mass, which is 0.01 kg multiplied by the specific capacity of water multiplied by the change in temperature, which the change in temperature is final minus initial. Final is 0 minus the initial, which is negative 15, like this, plus the mass, which is 0.01 multiplied by the latent heat of fusion, plus the mass again here, 0.01 multiplied by the specific capacity of your water multiplied by the change in temperature, which here the change in temperature will be equal to what? Will be equal to final, T final that we don't know, minus 0 degrees Celsius. This is on the left-hand side. Whilst on the right-hand side, you're going to have negative 0.1 kilograms multiplied by specific capacity of water multiplied by the change in temperature, which the change in temperature will be T final minus T initial, which was 30 degrees Celsius, like this. So you can use this way. You can just plug in the specific capacities and the latent heat capacities of the fusion in order for you to find your latent heat, or I mean your equilibrium temperature. It works like that, and they will never ask you questions that are actually out of context when it comes to this. You just have to follow this, know these things, and apply them when they are needed. And there is nothing actually very difficult about the concept of latent heat of fusion and also latent heat of vaporization.